Welcome back to Physics 371 Online. Today we're going to talk about some concepts that take the physics of Faraday's law and show how it has relevance in practical circuits. And this topic deals with quantities called mutual inductance and self-inductance. And because, as we've seen, changes in magnetic flux through a conducting loop produce an EMF, this means that circuits that have changing currents have an effect on nearby circuits. And as we will see, they even have an effect on themselves. So first, let's consider the case of two coils of wire that are nearby but are not electrically connected. And as this sketch shows, you've got a coil number 1 on the left-hand side that has a power supply connected to a coil of wire, and then it's wrapped around what is schematically shown here as an iron rod, but it's not electrically connected to the second loop, which consists of its own set of coil wires that are just connected to a voltmeter so that we can test to see whether any current flows in this second loop. So what happens then is initially there's no current flowing in the first loop, but as we close the switch, current begins to flow. So initially it's a current of 0 and it ramps up to eventually a final current. But while the current is changing, this changing current I1 produces a changing magnetic field that's experienced in the middle of loop 2, and we'll call that B2. So if B2 is changing, that means there's a flux through coil 2 that's also changing. And we can show the proportionality between these quantities as follows. We can say that the flux experienced in the middle of coil 2 is of course proportional to B2. To actually calculate that flux, we would have to do a complicated integral, but let's just be content for the moment with proportionality, so that we can see that B2 is proportional, of course, to phi 2 is proportional to B2, and B2 is proportional to I1, which was the current initially flowing through coil 1 that produced that magnetic field. And so we see that there's a proportionality between the flux phi 2 and the current that produced it, I1. And what we do is define a proportionality constant between those two that's called the mutual inductance. Phi 2 is equal to a constant M21 I1. And the subscripts on M tell us that it's the mutual inductance between coil 2 and the flux is in coil 2 produced by coil 1. So with this definition in place, we can now just apply Faraday's law and write an expression for the EMF that's induced in coil 2 because of the current flowing in coil 1. So we start with the equation from the previous slide, this definition that introduces the proportionality constant of the mutual inductance. Faraday's law now tells us that the EMF that's induced is minus the time derivative of the flux, and so the M21 is simply dependent on the geometry of the two coils. And as a result of that, it doesn't change in time. So that can come outside of the time derivative, and we have the expression for E2 that's just minus M di dt. So we can also imagine doing this experiment in reverse with the same geometry, but now having coils, a current flow through coil 2, and the same kind of thing will happen in reverse. While that current is changing, ramping up from 0, there will be a similar EMF in coil 1, and if we just change the subscripts, we see that the EMF induced in coil 1 would be, of course, minus the time derivative of the flux through coil 1, which in this case would be minus M12 di2 dt. And M12 and M21 are distinct quantities. They would result from different experiments, but one of the really cool things that we can show is that those two proportionality constants are the same as long as the geometry has not changed. And as a result of that, we usually write this proportionality constant without any subscripts, even though being a mutual inductance, it actually applies to two coils placed in proximity to one another. But it really doesn't matter which one the current is flowing through, the effect will be the same. So Now imagine that there's only one coil. Okay, we've looked at the case of two coils, and that makes sense. But what if there's just one coil? So I've just chopped the previous diagram in half, and now I want to ask the question, what happens when we close the switch here? And it shouldn't take too much thought to convince you that as current I1 begins to flow around coil 1, of course, looking kind of like a solenoid, there will be a magnetic field set up inside coil 1 itself. And while the current is changing, as it's ramping up from 0 toward its final value, that magnetic field will be changing, which will produce a changing flux. And by Faraday's law, that changing flux leads to an EMF in the coil itself. So we don't even need to have two coils in order to detect the influence of Faraday's law. This phenomenon is called self-inductance because the current flowing through the coil induces an EMF in itself. We can quantify this very similar to the way that we did for the mutual inductance by noting that there should be a proportionality between the flux through coil 1 and the magnetic field set up in coil 1, and that magnetic field, of course, depends on the current. So if we define a proportionality constant between phi and I, we'll call this L by convention. L is the self-inductance of this coil, and again it depends on the size and the shape of the coil. But once we've made this definition, we can go back to Faraday's law and drop the subscripts here because now we've really only got one coil. There's no point in having separate subscripts. So this EMF is minus L di dt. So that's a nice expression that is often used when we want to calculate the influence of a changing current on an electrical circuit. So Lenz's law reminds us that whether we're talking about mutual inductance or self-inductance, since Faraday's law is involved, the EMF that's set up always opposes the changing current that created it. And in the context of a single coil, like what we have here, one single circuit, this kind of an EMF is called a back EMF. And it's a back EMF because it's a current, or the back EMF produces a current in the coil that opposes the rate of change of the original current. And so as we close the switch, rather than have the current I go from 0 to its final value instantaneously, it will actually take a short time to reach its final value because there is a back EMF that produces a back current opposite to the direction of the flow of this original changing current. And by the way, a circuit element that is often something like a solenoid, a coil of wire, whose purpose in a circuit is to reduce the rate of change of current, is called an inductor. You've probably dealt with those in previous circuit courses. And one thing I'll just note is there are some simple geometrical cases like an ideal solenoid where it's possible to calculate L or M if we have two such simple geometries, but in the laboratory usually the kinds of circuit elements that we have are with shapes that make it difficult to calculate, except in an approximate way, what that inductance really is. And so in practice, these kinds of quantities are usually obtained more easily by experiment. We might be able to do an approximate calculation to get an estimate of what the inductance should be, but it's more accurate to just do the measurement. Last topic then, in preparation for this class, has to do with the storage of magnetic energy. Now having explained how we get this back EMF, we can now ask the question, well, if we're working against something, when we close a switch and current begins to flow, we're working against something that's set up in opposition to that. So the work that's needed, we can calculate. The work that's needed in a circuit when we close the switch to build up the current from 0 to a final steady state current. And this work is actually a form of stored energy. We can call it magnetic energy. So we start with a definition of power. Power is the rate of change of work. And so in this case, the power that would be supplied by the power supply working against the back EMF would be minus I times the back EMF. And the reason for the minus sign is if we just had I times E for the back EMF, that would be the power that the back EMF produces. Here we want to work against that. We want to overcome that by using the power supply. And so the power supply is doing the work against the back EMF. So we can now substitute in from our expression from the previous slide for this back EMF. We know that that is minus L di dt. And so we're left with Li di dt as the expression for the rate of work done. And notice that on both sides of the equation we have a time derivative, so we could multiply both sides by dt and thereby find an expression for the differential amount of work done in causing the current, when it has a value of I, to change by an amount di. All right, so the differential amount of work needed to change the current by a differential amount we can write by simply solving for dW in this equation. And what we get is dW is Li di. The primes I put in here because in the next step I'm going to do an integral where I will calculate the total amount of work done when the current goes from an initial value of 0 to a final steady state value of I. So the primes remind us that there's a difference between the variable and the actual limit. So here to find the network, it's integral from 0 to I of Li prime di prime. That's a simple integral to do. The L is a constant. It comes outside the integral, so we're integrating I, which gives us I squared over 2, and we substitute in the limits and we get 1/2 Li squared, which represents then the amount of energy needed, or the amount of work done in order to overcome the back EMF. The larger that the self-inductance of the circuit or the circuit element is, the greater work is needed. It's interesting now to compare this to the expression that we set up before when we were charging up a capacitor using a potential difference V. And we get a very similar form for it. We get 1/2 C times V squared, so that the quantity that is relevant to energy storage in electric fields is the voltage, whereas the quantity that's relevant to energy storage by magnetic fields is the current. Otherwise, C and L play very similar roles in these two equations. There's also, just in closing, one last useful way of expressing the stored energy in terms of the magnetic field that's established inside the circuit element. And the result, when we consider how much energy is required to produce a magnetic field B, starting off, of course, with 0 magnetic field, has this form here. I won't show you the derivation, but it's not too difficult to do for a simple geometry. And it ought to look familiar to you because we considered something very similar earlier in the course when we were talking about assembling a collection of charges. And by moving them into a final configuration from an initial condition of infinite separation, we were able to establish an expression for the energy stored in that kind of a configuration. And that looked very similar. We had a proportionality constant epsilon naught over 2, and then the integral over all space was of the square of the electric field integrated over all space. So these two equations look very similar to one another. They function in a very similar fashion in the two theories. I'll leave you with one final question. It's relatively easy to see how we can get back the energy that we store electrically. For example, in a charged capacitor. We can charge up a capacitor, deposit plus and minus charge on the two plates, disconnect it from the power supply, and carry it around. And it's relatively easy to see how we can get that energy back. But in the case of magnetic energy, or energy stored in a magnetic field, here we flip a switch and current builds up from 0 to a final value, and somehow energy is stored in that final current flow. So the question is, how do we get that energy back? Can we get that energy back, and if so, how? I'll leave you with that question, and we will talk about that, among other things, in class.